Okay, welcome back. And today we're going to finish up chapter 19, and also we're going to do that. We're going to go cover section 3 on absorbing Markov chains. And so we're going to talk about what is an absorbing Markov chain. Then we're going to do some examples of how to deal with those. And one example of a like where we're going to run into an absorbing state or absorbing Markov chains is in the example of what if we have a gambler that is going to gamble until they either um, lose all their money or she um, wins a predetermined amount. Okay, so that, and we want to know what is the probability that she eventually will go broke. Okay, uh, so suppose we have a transition matrix. Okay, um, and we're going to look at some examples of um, tran- of of transition matrices of a P matrix where we can have some absorbing states, and what does that mean and how do we um, work with them. Okay, so before we go on, well, let's look at a couple of things here in this matrix. Okay, so let's look at this here. Okay, so we have a P matrix. Okay, and so let's see what the P matrix looks like. And so in this case here, our transition matrix looks something like this. Okay, so we have our transition matrix here. Okay, so notice that all the rows add up to 1, right? But notice that we've got some zeros here. Okay, and so we're going to use this, and so this is um, the transition diagram. Okay, for this shows what's going on from state to state, or from um, from one repetition to another repetition. Okay, so the matrix here shows that P12, the probability of going from state 1 to state 2 is 0.6, and that P22, the probability of staying in state 2 is 1. Okay, so thus once state 2 is entered, it is impossible to leave. And for this reason, the state 2 is called an absorbing state. Okay, because once you see all these states here, you've got you got a percentage of times where it's going to enter coming back, and you've got a percentage of times going out to either 1 or 2. But as soon as one of the states enters 2, there's nothing coming out. So 2 is an absorbing state. Okay, so if you end up going from state 1 to state 2 with a probability of 0.6, but once you get into state 2, then you're done. Okay, so that's what we call an absorbing state. Okay, so state I of a Markov chain is an absorbing state if PII is 1. Okay, so notice in here P22 is 1. Okay, so that means it's an absorbing state. Okay, also absorbing Markov state is an absorbing chain. So absorbing Markov chain is a Markov chain. A Markov chain is an absorbing chain if and only if the following two conditions are satisfied. One, the chain has at least one absorbing state in it. At least one absorbing state. Okay. And two, it is possible to go from any non-absorbing state to some absorbing state, perhaps in more than one step. Okay. So it could be more than one step. For example, from step 3, you could go to the absorbing state in one step, or it could take you 2 steps, or it could take you 1, 2, 3 steps, okay? Or 1, 2, 3, 4, 5 steps, okay? So it just depends on the number of steps, but eventually you're going to end up in a finite number of steps, or maybe in some number of steps into the absorbing state, okay? So it is possible, not that it will happen, but it is possible to go from any non-absorbing state to some absorbing state in more, in certain number of steps. Could be one step, or it could be more than one step, okay? So now, if we look at this example here, okay, we want to identify all of the absorbing states in the Markov chain having the following matrices or matrix, okay? Decide whether the Markov chain is absorbing, okay? So in this case here, what do we have? We've got the chain, so let's do the chain here. Okay, so what's the chain? So, or not the chain, but here's the P matrix. Okay, so again, we've got 3 states. So the P matrix is going to be this. Okay, so this is the P matrix. So now, does it have at least one absorbing state? Yes, it does. It has 2 of them, right? So here you've got P11 is 1, and you've got P33 is 1, and the rest are zeros. So these are 2 absorbing states, and you can see from the diagram here, from the transition diagram, you've got 1. So as soon as you enter state 1, there's no little arrows going out of state 1. It's 1. And the same thing is true for state 3. Okay. And is it also true that you can enter from a non-absorbing state to an absorbing state in one or more steps? And the answer is yes. So I can go to this one in one step, I can go to this one in one step, or it could be more than one step. So it is possible to go from 2 to either 1 or 3. Okay, so this is an absorbing Markov chain. Okay, now, what about this one? So here, we've got a couple of things going on. Okay, so let's draw this matrix. Okay, so let's draw this matrix here. So this is going to be okay. So now we've got, what do we have here? We've got and what else do we have? We've got this, and then we've got this, and then we've got, oops, Okay, so here's what we got going on. Okay, so now, what do I have here? So this means that I'm going from state 1 to state either 1 or 2, but I'm not going to the other two states. So state 1 either goes to state 2 or goes to itself. And then this one is an absorbing state because at 2, 2, it's a 1, so everything else is 0. So once you enter 2, you're staying there. It's like a black hole. You're done. You're staying there. And then state 3 is also an absorbing state. And then you've got the state 4, which only goes between 3 and 4. Okay, so it'll go to itself or to 3. Okay, so notice that there's nothing going between these two. Okay, so it doesn't meet the conditions for the Markov chain. Now, so if we look at this, so first of all, are there Markovs, or are there absorbing states? Yes, there are two of them. State 2 and state 3 are absorbing states. And also, what else? Is it possible to go from a non-absorbing state to an absorbing state? Well, you can go, this is a non-absorbing state, and it is possible in one or more steps to go to a absorbing state. And likewise, it is possible to go from this non-absorbing state to an absorbing state. Okay, so these are, this is another example of an absorbing Markov chain. Okay, let's see here. Okay, what about this one? Okay, and so in this one, what do we have? So let's draw the matrix, the transition matrix from here. Okay, so what do we have? We have 0.60, 0.4. And then we have 0, 1, 0, 0. And 0.9. And then we got okay. So now, so this is the P matrix, okay, and this is the diagram for it, okay. So notice that, what do we have here? We've got two states here. So one, are there absorbing states? Yes, 4 and 2 are absorbing states. 2, is it possible to go from a non-absorbing state to an absorbing state? And the answer is no, because these two are only going between two non-absorbing states. So it is impossible to enter into an absorbing state in this case. Okay, so in this case, this is not an absorbing Markov chain. Okay, this is a non-absorbing Markov chain. Okay, so in this case here, it is neither non-absorbing state. So this is not an absorbing Markov chain. So we would say it's a non-absorbing Markov chain. Okay, so now we want to identify all the absorbing states in the following transition matrix. Decide whether the Markov chain is absorbing. Okay, so now, are there absorbing states? The answer is yes, right? So we've got an absorbing state here at 1 and another absorbing state at 3. Next question, is it possible to enter from one of the other non-absorbing states, is it possible to enter the absorbing states? Well, if we look at 2, okay, all we have to do is go to, is it possible to go from 2 to 3? And the answer is no. Is it possible to go from from 4 to 3? And the answer is no. So this is a non-absorbing Markov chain. Okay. Oh, I messed up. So here, I forgot about these. So you can go to 1. So it is possible to go to an absorbing state. So it doesn't have to be this absorbing state, but they do go to 1. So this is a Markov, an absorbing Markov chain. I forgot about the other one. So we have this one here and this one here. So again, just make sure that you check those. Don't focus on like the one I did, which is this one. So there are 2 absorbing states. So as long as you can get from one non-absorbing state to another one. So in this case, even though we can't get to 3, or we can get to, excuse me, yeah, even though we can't get to 3 from either one of the non-absorbing states, we can get to 1 because there's a probability of greater than 0 to get to that one. So it is possible that within a certain number of steps, maybe more than 1, that we could get to those. Okay, so now here are the properties of an absorbing Markov chain, if it is indeed absorbing. 1, regardless of the initial state, in a finite number of steps, the chain will enter an absorbing state and then stay there in that state. 2, the power of the transition matrix gets closer and closer to some particular matrix. Okay. And 3, the long-term trend depends on the initial state. So notice that this is different than before in the regular Markov chain, okay, where we said the long-term trend is independent of the initial state. Now, if it's an absorbing Markov chain, then it is dependent on the initial state. So the initial state will affect the long-term trend, or what the V matrix will be. Okay. So now let P, let P be the transition matrix for an absorbing Markov chain. Rearrange the rows and columns of P so that the absorbing states come first. Matrix P will then have this form where we have different quadrants. Okay, so we'll have this I of M, which is like a small identity matrix. Then we'll have an O matrix, an R matrix, and a Q matrix. Okay, but it has to be in this form. Okay, this is the identity matrix where M equals the number of absorbing states. O is just a matrix of all zeros, because obviously this is going to be zeros, because you'll have this identity matrix here, which means it's going to be the rest of the entries are going to be 0 after this identity. And then you have an R matrix, okay? And then you have a Q matrix. So the fundamental matrix is defined as F equals I of N minus Q inverse. So this is the inverse of whatever this matrix is. Okay, so we do I of N minus Q. Okay, where I of n is the same size as q. The element in row I, column j of the fundamental matrix gives the number of visits to state j that are expected to occur before absorption, given that the current state is I. Okay, again, the element in row ij, okay, so this matrix, this fundamental matrix, the element that's in ij tells us the number of visits that are expected to state j before absorption, given that the current state is I. Okay, the product FR, so F times R, gives the matrix of probabilities that a particular initial non-absorbing state will lead to a particular absorbing state. Okay, so again, this may make no sense to you right now, but we're going to do some examples here. Okay, so let's see here. Let's see here. Oh, okay. I don't have any examples. I don't have any examples on here. Let's see if we have this. Oops. Okay. Do we want to use this one? Okay, so this is a I don't want to use this one. So this is for teacher retention. So this is a Markov chain. Well, it's definitely an absorbing Markov chain. You've got these absorbing states here. You've got this one, this one, this one. This. Eight. Okay, so you've got. Okay. Yeah, let's not do this one here. I'll tell you what, we're going to do a couple of examples in class. You know what? Actually, let's look at one. Oh, I guess it's not going to, well, let's see if it works. So here's the setup. So we can break this up into the 4 quadrants, right? So this is our identity matrix. This is the matrix of zeros. This is going to be our R matrix, and this is our Q matrix, okay? Just like down here, okay? So we're going to take this minus this. So for the gambler's ruin problem, we're going to use I5. See here. Okay, so you redid the matrix here, right? Remember we moved the absorbing states up to first in place. So there's our state 0 and state 6. So always remember the states. Okay, so it's always helpful to write the state numbers here when you're doing this. Okay, so now if we look at the gambler's ruin, we look at the identity matrix, I5, since Q is 5, right? So Q is a 5 by 5 matrix, so we're going to use I5. And then we're going to subtract these two, and then we're going to take the inverse of these. So we end up with the inverse of this, and the inverse matrix ends up being this. Okay, and so again, you remember how to take the inverse of a matrix. Okay, so again, either use your calculator at this point, but make sure you know how to do it. Okay, so now what this does is the fundamental matrix gives the expected number of visits to each state before absorption occurs. For example, if player A currently has $2, okay, so let's say A has $2, okay, then the second row of the fundamental matrix just computed says that she expects to have $1 on average 1 1/3 times. Okay, 1 1/3 times before losing all her money. Okay, and she'll have $3 twice. Okay, she'll be at $2. What? 2 2/3 times, right? And so on and so forth. Okay, so now the total number of times that player A expects to have various amounts of money before quitting the game. Quitting the game is the sum of the entries in the second row. So if we add up all of these entries in the second row, then what do we get? We get 8. So basically, there are going to be, in other words, if player A is currently $2, then in about 8 more turns, either she or player 8 is going to go broke. Okay, so at this point here, if you are in state 2, you have $2, then pretty much you're going to either lose your money or player B is going to lose their money within eight turns. Okay. Okay, so let's see. I think that's all we're going to do. And I'll do some more examples in class as well.